Challena Pinckney, and my mentor for my research was Dr. John Price. And I'm trying to identify subsurface granites of the southern Oklahoma Aulacogen using microanalysis. First, before anything else, I would like to talk about the southern Oklahoma Aulacogen, which we call SOA for short. The SOA is a failed continental rift that happened 530 million years ago. The SOA actually is not all in Oklahoma. It stretches from North Texas all the way to eastern Utah. Most of the SOA is in the subsurface except for except for the Wichita Mountains, and this is a picture of Mount Scott. All this is exposed SOA. Now, to really show you how much it is underneath the subsurface, I'm going to show a map of Oklahoma. Now, this little green part right here, that's the Wichita Mountains. That is exposed SOA, so everything else is in the subsurface. So, how are we going to get what we need? What we're going to do, or first of all, this is where we are working at, just in the Arbuckle Mountains. And like I said, everything's in the subsurface, buried by younger sediment. So what we did is we took drilling wells from previous oil and gas exploration, and we took their samples, and I have two or more depths for each well to analyze. And here's where our wells are. This is Union Morton, this is Morrow, Turner Falls, Sparks Ranch, and Chapman. So what is my question in hand? I mean, when you look at the Wichita Mountains, you can tell the different magma bodies or plutons on the surface, but we want to know if we can see the plutons in the subsurface with the limited data that we have, which, we can using our friends, the granites. This is an intrusive igneous rock, which mainly consists of quartz, and your pink stuff, or the feldspars, and the dark minerals in here are your micas and amphiboles. What we really need from him is the amphiboles. The reason behind that is because your quartz, your feldspar, and your mica pretty much has the same chemical composition except for your amphiboles. Your amphiboles it's what we call a trash can mineral, and so it will take in the elements that are in the magmas that they are created in. So our amphiboles are a dark chain silicate mineral. Our amphibole of choice is our hornblende. This, in our area, this is mainly what our amphibole is. Some of the chemicals that can vary in amphiboles are your potassium, your calcium, sodium, iron, magnesium, aluminum, and silicon. And another thing I would like to mention before I get into my prep and my data is the size of our samples. To the right here, to the left, is pretty much a good chunk of granite what you can find in the in the surface. Now in the subsurface, like I said, we had to use drilling fragments from the just well samples. So compared to this, 50 millimeters across to 2 millimeters, so it's very tiny. So with that said, we have to do a lot of prep to shoot them with our laser. So what we do is we weigh our sample, and then we take a picture using a video microscope to keep record of what the granite actually looks like. After that, we take about 8 to 10 samples to mount. Now, out of those 8 to 10 samples, we have to pick out the ones that have the dark mineral showing, like this one right here. I would pick this one. And then before we mount them, we weigh the remaining fragments that we did not use so we can have record of how many fragments we did use. So with the fragments that we are using, we mounted them with 2-part plastic epoxy. It takes about 24 hours to dry, so once they are dried and ready to go, pop them out of the little red things up here, and we grinded it down to make sure the surface is flat so we can shoot the laser. Now, what is the laser I'm talking about? It is the laser-induced breakdown spectrometry. What it does, it shoots a laser to your sample, or onto your sample. It heats it up, creates a plasma, and that plasma emits light, and the instrument picks up the peak elements and creates a spectral analysis. And what it leaves behind is a nice little crater. And this picture below is a picture of our machine. Right here, this is our cooling system. This is the laser itself that does the analysis. And then, of course, it transfers to our computers. Now, before we can actually shoot, we have to take pictures of our samples. So the reason for that is so we can see where we're at. And then our second photo here, all these dots, this is where I actually shot the laser. We have to record where we shoot the laser, reason being if we need to go back, we need to see where we shot the laser, and as I go on my talk, you can see that we need it to see, if we go to different machines, we need to see where we actually shot. So you take the picture, you make sure all your settings are correct, and then I'm going to use this spot for my example. You pick from the dark minerals, because that's what we're looking at, and you shoot it with kind of a clear shot, and it gets all the debris and everything you do not want in your analysis, and then you shoot it 25 times. After it's shot 25 times, it averages all 25 shots into your spectral analysis. And this one, which I think it is this shot right here, this one has a high sodium peak as well as magnesium. Everything below here is just background noise. So after you do all your shots and get all your data, you go to Excel and you compile everything, and then you get an average of all your points at each step. After that, you use R program, which this is what this is. You use the R program to get your principal component analysis, your PCA graph. Now it takes a little bit of work to make it look pretty, and there's my pretty one. So right here, what you're seeing, you see all my wells, but the numbers corresponding with my wells is the depth in feet underneath the ground. So with this, if everything was to be the same, it would plot right here at 0, 0. But everything is not the same. So it differentials out. Well, another thing we can see is that, I'll use Turner Falls as my example, that everything is plotting over here. So you can see that there's something similar in the Turner Falls samples. But there's one thing. We have an outlier. That outlier is nothing like our other samples. So how can we further analyze that? What can we do? Well, that's the reason why Dr. Price and I went to Norman, Oklahoma to play with this lovely machine. This lovely machine is called electron microprobe, or probe for short. It's an electron microscope. It gives really robust analysis. The only thing with this compared to our laser is that this takes longer to prep your samples. You have to actually polish it, make it look like it's glass on that granite side. And another thing is that when you try to find your spots, it takes the whole day, because during that time you can see this image right here. This is for my example. This is Turner Falls 9340, and this is a photo of the backscattered electrons, which you can tell it's kind of like a grayscale, which the grayscale corresponds to the density of the material that's in there. And the lighter the color, the denser it is. So right here, you have your oxides, which is going to be denser than your quartz. And with this, it also gives you quick analysis, so it reveals general composition. And what we found out is that our amphiboles, that, or at least what we thought were amphiboles, were actually chlorides. So we went back to our PCA map and took out the outliers, because now we know they're chlorides. And then one thing further, what I did is I split it on the zero line to negative and positive, and you can see, for example, you have your Sparks Ranch on this side, and Union Martin. On the other side, you have the rest. So I decided I wanted to go back to my map and look at the geography, and we noticed that Union Martin, all the negative, was to the west, and then everything else was to the east, showing that we could potentially have two plutons in the subsurface. This graph is showing the silicon versus magnesium, and this is what we got from the data from the probe. And this shows that Sparks Ranch, it has higher silicon and magnesium compared to Turner Falls and Morrow, and this indicates that there is two amphibole bodies. So in my conclusion, our laser can determine subtle differences in amphiboles. I mean, this permits rapid analysis of small fragments from the drilling. Determining our chlorides still remains a problem. We're still working on that. But we found out, with the probe in Norman, we can assist the analysis. But from my data, we can see that there is clearly two different amphibole populations in the subsurface of the Arbuckle Mountains. And this potentially indicates two individual SOA plutons. Any questions?